Okay, good morning, class. Good morning once again. Today we're going to start our discussion on multiple linear regression. Now, there are some discussions, there are some pointers, there are some points that we haven't discussed with data wrangling, deep layer. I'm going to record those portions and also the descriptive statistics and post it in our canvas for you to watch, for you to view. But today we're going to start with one of the main topics in our subject, which is multiple linear regression. So I shared with you this file. Kindly open it. It's in the Introduction to Regression workbook. It's a workbook because the codes I did not put the codes. You'll have to write it as you follow along. So you had subjects before where you discussed multiple linear regression. Okay, we'll just abbreviate it to MLR, also known as multiple linear regression. And as I said here, I have some brief notes here. It's a statistical process. It's a statistical technique where you try to explain, describe, or predict a variable of interest called the dependent variable, okay, using either one explanatory variable, otherwise known as independent variable, or several. Okay, if you only have one independent variable or explanatory variable, you call it a simple linear regression. If you have several variables that you're using in order to explain or predict your response variable, then you call it multiple linear regression. Okay, as we said, the goal of a regression model is to explain or establish the relationship between your dependent variable, okay, or your response variable with your explanatory or independent variable. Okay, so as I mentioned a while ago, if you're only using one variable to explain your response variable, you call it simple linear regression. However, if you have several, then you have what we call multiple linear regression. Okay, so I think, okay, the formula, okay, I'll just, okay, this is an example of okay, this is what we call latex, LATEX. This is a code, okay, that's in latex, and it generates this. This is the output. If you take a look at this, I'll just give an explanation. So here you have the dollar sign here indicates that this is the beginning and this is the end of this code. Okay, and then here backslash begin, and there's some codes here aligned, which means that the lines should be, okay, the line should be aligned like this. Okay, and then here you have y underscore I. So this means this is subscript. So take a look at the printout here, y underscore I. Okay, so you will in your take-home exams, you'll be you need to learn some of this, but not all. Okay, for example, you need to learn how to write beta sub 0. So it's just this one. If you're writing a Greek letter, it's backslash beta, and then the sub is underscore 0. So this one is beta sub 0. Okay, so if you know this, then it will be easy to write also beta sub 1. Okay, so you can see here x, and this is underscore, which means this is subscript. No, if you have several letters for your subscript, you put it in curly brackets, etc. Okay, so if you write this, okay, you'll notice that this is the main output. This one. So it's a very good how should I say it, formatting of this text. So a multiple linear regression, the equation of which is y sub I. So this is your response variable. This is your dependent variable. it's equal to a certain constant beta null, which we call the intercept, plus beta 1 times x sub I 1 plus x sub I beta 2 times x sub I 2. Okay, the i's here, y sub I, x sub I, x sub I refers to the different observations. Okay, so we have y sub 1, that will be the first observation, y sub 10, that will be the 10th observation. And then here you have x sub 1. This means this is the first independent variable. Then you have the second independent variable up to the nth independent variable plus a certain error term. Okay, so here it specifies here that I is equal to the n observations, y sub I is your dependent variable, x sub I is your explanatory variables, beta null is your y-intercept or constant term, beta n is the slope coefficient for each explanatory variables, and epsilon is the model's error term, also known as the residual. Okay, so we'll go through this as we go along. We'll try to understand what this equation is all about. Okay, any questions so far? So you notice how how this text here was written here. The double line here simply means that you write it in the next line. Okay, this double line here, double backslash. So you see yung where, diba? Here where it started with the next line. So that's the double line. All right. Now, if you recall in your previous maybe statistics class, there are certain assumptions that have to be let's say followed, or that has to be the term for that is satisfied. Okay, so there are certain assumptions that have to be satisfied when you're doing multiple linear regression. When these assumptions are not satisfied, then we have a problem. Okay, some of these assumptions are the following. Number one, the linearity of the data. Okay, what do we mean by that? Linearity of the data. Well, linearity of the data means that the relationship between your y and your x has to be linear. Okay, so for example, if you plot y, let's say you plot your dependent variable y and your independent variable x, the relation between them has to be, let me change the color of this, has to be somewhat linear. Okay, just like this. You can see here the relationship is about linear. Okay, and it cannot be something like this. If the relationship was like this, if you plot x and y and it turns out to be like this, then you notice that there's not a linear relationship, but rather a sort of a quadratic relationship, okay, between x and y. So when you're modeling, when you're using multiple linear regression, the relationship between your dependent variable y and your independent variable x should follow a linear relationship. Otherwise, if it's following, for example, a relationship like this, okay, we have a polynomial relationship, then the multiple linear regression will not, it will violate the first assumption, linearity of the data, and that will make your model unfit. Okay, we cannot use multiple linear regression if the relationship between your y, your dependent variable or your outcome variable, and your x, your independent variable or your predictor variables, is not linear. Okay, any questions about that? Is that clear, class? So first and foremost, there should be a linear relationship between your y and your x. Otherwise, if the linear relationship, if the If the relationship is not linear, then it would be not a good idea to use multiple linear regression model. Then you will have to use other types of model in order to establish a relationship between your y and your x. Clear, class? Kindly chat, please, if that first assumption is clear. All right, thank you. Okay, good. Thank you for the feedback. Next assumption is linearity of the parameters. Okay, what do you mean by linearity of the parameters? This one. When you take a look at the model, linearity of the parameters mean that your coefficients, this ones, okay, they should be linear. Okay, which means that you cannot use, for example, you cannot use the square root of beta. Okay, you cannot use 1 over beta. You cannot use the log of beta. Okay, so that's what we mean by linearity of the parameters. These are the parameters, the beta 1, the beta 2, the beta sub n's. They are the parameters. Now, I'm not saying that, we're not saying that the independent variables cannot be logged. Pwede. You can get the log of x. Okay, for example, you have this equation, y sub 1 is equal to beta null plus beta 1 times the log of x, that can be, plus beta 2 times the square root of x. It's okay to do that. But you cannot use the log of beta 1 or the square root of beta 1 or the 1 over b times beta 1 over b sub beta sub n. Okay, that's what we mean by the linearity of the parameters. Because if you have this equation, then it will be not possible to solve for your betas in this, or it will be very difficult to solve for your betas if you have this format. Okay, so your parameters should be in, let me just clear that, linear. So that's what we mean, class, by linearity in parameters. Okay, this one, linear. Assumption 2 requires the specified model to be linear in parameters, but it does not require the model to be linear in variables. That's what I meant a while ago. Okay, what do I mean by linear in the variables? You can get the log of x1. You can get the square root of x1, no problem about that. But the parameters beta 1, beta 2, beta 3 should be linear. Okay, let's take a look at this. This is another equation here. We have this model, y sub I is equal to beta null plus beta 1 squared. Okay, this is what I was telling you about. Okay, this is not linear in the parameters. So beta 1 is squared. Okay, assumption 2 of the classical CLRN means classical linear regression model requires the model to be linear in parameters. OLS, by the way, is the method by which we solve for the parameters. OLS, or ordinary least squares, is not able to estimate equation 1 in any meaningful way. However, assumption 2 does not require the model to be linear in variables. Thus, x sub 1 here can be squared, no problem about that. Okay, so take a look at this, another equation, this one. Y sub I is equal to beta null plus beta 1 x sub I squared. Okay, so this is okay, this is acceptable. Okay, but not the parameter being squared. Okay, so let me see. Okay, so any questions about assumption 2? All right, no questions? Okay, thank you. Third assumption is homogeneity of residual variance. Okay, what do we mean by this? When we generate a model, okay, what we have to do is to plot our residuals. Residuals are the differences between the actual value and your model value. Okay, so let me just illustrate that. Suppose we have this model, okay, and when we already are able to compute our parameters, our betas, which means that we have already our model, what we can do is we can compute for our y hat. Y hat is our predicted value. Okay, y hat sub I means we we substitute the betas. Okay, since we know the x's, we know the predictors, so we're able to come up with the predicted value. Let me repeat that. Once you know the parameters beta 1, beta null, beta 1, etc., then we can substitute that in the model, okay? And then we can have what we call the predicted value. The predicted value is obtained by using the model and then solving for your y. You notice I place here y hat. Y hat stands for your predicted value, and it's obtained by using the parameters, the parameters that we generated, and substituting that in our model to get our predicted value. Okay, now the predicted value oftentimes will not be equal to the actual value. Because we have the actual value, we have the data. So we have, say, y sub 1. What's y sub 1? Say, for example, it's 35. And then we have this predicted value, y hat sub 1. Let's suppose our y hat sub 1 is 34. So you notice that there's a difference between the actual value and the predicted value. And the difference between this is your epsilon, your residual. Okay, so I hope that's clear. When we generate our model, we will be able to have our predicted values, and then we're going to compare it with your actual values so that we have now a vector of residuals, a vector of error terms. Okay, the vector of error terms will be the difference between your actual value minus your predicted value. Okay, and when we plot the residuals, okay, so for example, we're going to plot the residuals. Let me just go here a bit. Okay, so this is our, let's say this is our residual. Okay, sorry, this is our residual, this is our epsilon. Okay, and this is our x value. When we plot this, the residual should behave in such a way that it's random. Okay, like this. It's random. So notice that the residuals, if we are able to draw a line here and here, okay, over this value of your predictors, it has constant mean. The average of your residuals is constant. And also it has constant variance. Okay, when we say constant variance, it does not go out of this band. It does not behave like this. It's not going up, or it's not going down. Okay, so that's what we mean by homogeneity of the residual variance. Okay, in other words, the residual should be homoscedastic. When we say homoscedastic, it means constant variance and constant mean. Okay, here, if we get the average of this, of this residuals, notice that the mean is constant. Also, the variance is constant. If the variance is not constant, then the residuals will behave like this. So it's either going up like this, or the residuals are going down like this. It has a trend. So if the residuals behave like this, either going up or going down, that means that the residuals are not constant. They don't display constant variance. So in that case, we have the residuals to be heteroskedastic. Okay, heteroskedastic. And we don't want that. We don't want the residuals to be heteroskedastic because it means that our model is not able to capture that going up movement or going down. Okay. Again, let me pause for a while and seek your feedback if we're clear about that third assumption. Our residuals should be homoskedastic, which means constant dapat yung variance. So dapat walang panning out. Okay, let me show that. Kasi kung yung residuals natin, pag ganito, ibig sabihin, across the independent variable, nag-i-increase siya. We call this the fanning out. No? It's like a fan. Lumalaki siya across a higher value of your x, or it can be fanning down, pabaliktad. Then that means that your residuals are dependent on your x. Sabihin, yung model natin, hindi pa nakaka-capture yung dependency na yan. So dapat, yung residuals natin, they should be random. We call it white noise na lang. No? Hindi na natin mamamodel yan yung residuals na yan. Okay, any questions? Okay, pag heteroskedastic, thank you for that question, Conrad. If it's heteroskedastic, when you plot the residuals, they behave in a certain way, no? Parang ganito. Yan. When you, for example, we plotted the residuals, tapos yung residual plots natin, nagfa-fan out. Yan. Habang lumalaki yung x natin, lumalaki din siya. Diba yung variance natin, yun, no? Hindi constant. Yan. Behaves like this. The variance keeps on increasing. So this is indicative that your variance is not constant. Okay, so if the variance is not constant, then that's a phenomenon called heteroskedastic. Ang skedasticity, it means spread. Homoskedastic means equally. Equal kasi yung homos. No? Homo means the same. Skedastic means spread. So the spreading of your residuals is constant. Pag heteroskedastic naman, yung spread out niya is not constant. So either it's increasing or decreasing. Okay? Pag decreasing kasi, nagpa-fan in siya pag ganyan. Yan. So dito siya, pag ganyan yung residuals natin, then while the x is increasing, lumiliit yung residuals natin. So this is non-constancy in variance, residual variance. This is also not constant, hence it's called heteroskedastic. Okay, so let me again pause. Clear ba so far? Yung assumption number 3 natin, residual should be heteroskedastic. Okay, good. Thank you. Okay. Now these are very important kasi it's not enough that we're able to. It's easy using R to generate your model. I'll show you in a while, no? Dali-dali mag-model sa R. LM function na yan. Tapos may model na tayo. Pero it doesn't stop there. You have to check. We have to check our model if the assumptions of classical linear regression model are satisfied. Otherwise, if not, then we will have to address them. Hindi pwedeng, kasi if the assumptions are not satisfied, then hindi reliable yung model natin. Okay, our model is not reliable. It's not good to predict values of the dependent variable using that model. All right, let me clear our drawings. Okay, next we have the fourth. All right, explanatory variables are not collinear. What do we mean by this? Explanatory variables are not collinear. Okay, let me explain that. We want that the relationship between your y and your x to be collinear. Gusto natin strong yung linear relationship ni y at saka ni x. So that when you use x to predict y, you'll be able to establish this linear relationship. However, we don't want that the relationship between x and x, so x1 to x2 to, we don't want them to have a very strong linear relationship. Okay, yan. Nangyari yan. Very strong linear relationship ni x1 at saka ni x2. Now, why is that? Why don't we want x1 and x2, the independent variables, to have a strong linear relationship? Okay, which we call, pag strong yung linear relationship nila, we might be suffering from what we call multicollinearity. Why? Kasi it's possible that x1 and x2 are explaining the same thing about your y. So why will you use both of them to try to explain y when they're explaining the same thing? If they're highly correlated, then perhaps you just use one of them. Let me illustrate the case. Kunyari y, kunyari x1. No? You have x1 and then x2. This is x1. And x2 is simply equal to 3 times x1. All right. This is a very dramatized example. So you have your x1 here. Kunyari you have 2, then 4, then 1, then 7. These are the values in 8. And then your x2 is just 3 times x1. So whatever value of x1 is, you multiply that by 3, then you have x2. If you plot these two, perfect yung correlationship nila, no? It will be a straight line. Yan. Okay, it will be a straight line. So when we're going to use x1 and x2 to predict y1, okay? Let me explain it in Filipino. They will, quote unquote, mag-aaway sila sa pag-explain kay y. In other words, they will compete in trying to explain y, so that hindi natin alam kung which of these two variables, which are perfectly collinear, perfectly correlated, are trying to explain y. But as much as possible, we don't want the independent variables to be correlated. We want the independent variable to be correlated with the dependent variable, but not the explanatory variables, the independent variables, to be correlated with each other. Okay? Otherwise, if we have that scenario, we might be suffering from what we call multicollinearity. And this may be a problem. Okay? Okay, so this is a problem. This is the assumption that predictors are not too highly correlated with one another. Multicollinearity exists when the two or more of the explanatory variables are highly correlated. This is a problem because it will be hard put with this to disentangle. Okay, so x1 and x2 are trying to explain y. So which part of the variance of y is being explained by x1 or x2? So that can be a problem. So we don't want to be using variables that are highly correlated in trying to explain your dependent variable. Okay, why not just use one of them? Okay, also a parsimonious model will require that the less number of predictors, the better. Kung kaya nating i-explain si y using two variables, why use 100 variables to explain y? Diba? Okay, and later on we will see that there is a what we call penalty for using so many independent variables to explain your dependent variable. We will look at some metrics like Akaike information criterion, other information criterion that's used, to determine in comparing two models. Okay, so if you keep on using so many variables, then you'll be penalized with the information criterion measure AIC. Okay, next, independence of the residual terms. That's number 5. So the residual terms, as I mentioned a while ago, should be independent. Okay, what's an independent residual terms? They don't display a pattern, just like what we said a while ago. Okay, the residual should be random. Okay, so this is what we call a no pattern, no? Wala siyang pattern. Random siya. Constant yung residuals, constant yung mean niya, constant din yung variance niya. This is what we call residual terms. That's we call it white noise, no? Yung walang pattern siya. Residuals will have independence if it displays a pattern. Kunyari, pag ganito yung residuals, di ba, pataas. If the residuals are behaving this way, then may relationship sila, hindi sila independent. They are dependent kasi may pattern pa dito eh, di ba? So when we plot the residuals, they should not show any independence at all, which means the residuals should have constant mean and constant variance. All right? So tinignan natin, no? The residuals should have constant mean, constant variance. That means they are independent. And number 6, normally distributed. The residual should not show this type of a behavior, not normally distributed. Otherwise, mababiolate yung assumption natin, and then which means that our model is not fit. Okay, our model is not fit to describe your dependent variable y. Okay, so let me pause for a while. Any questions so far, class? So quick review. Number 1, dapat linear, no? Linearity in the relationship between x and y. We want y and x to be linearly related. If they're not, then, for example, polynomial or quadratic relationship nila, then we're not going to use a linear regression. Ibang regression ang gagamitin. Pangalawa, the parameters, yung betas. When we model the betas, they should be linear. Hindi ba pwedeng square root of beta o square root log of beta. Kailangan linear yung beta natin. Third assumption, okay, residuals. So marami sa residuals, dapat homoskedastic siya. When we say homoskedastic residuals, ibig sabihin nun, residuals have constant mean and constant variance. Okay, also the residuals should be normally distributed, yung number 6. Also, the residuals should be independent of each other. So dito, 4 yung tinitingnan natin sa residuals. Constant mean, constant variance, independent of each other, hindi sila correlated, and fourthly, normally distributed. Right? And then also, the explanatory variables should not suffer from multicollinearity. Okay? So those are the important assumptions. Okay? If these assumptions are met, then we have what we call, so let's go dito, no? We have what we call blue, no? A blue model, which is, okay, ito yung target natin, blue, which is the best linear unbiased estimator. Okay? Blue means best linear unbiased estimate. Otherwise, kung may violate these assumptions, then we will not have this best linear unbiased estimator blue. No? So take note of that. All right. So here I have given some okay. So tingnan natin to. I have given here some references. Okay, let me just show this. Okay, I will assume, class, that you also look at this. Okay, let me just show one of them. Okay. Key assumptions of OLS. Alright, ito yung assumptions natin. No? Yan. What we have mentioned a while ago. Assumption. Okay. Linear in parameters. Ito yung sinabi natin kanina. When the dependent variable is a linear function of independent variables and the error term, the regression is linear in parameters and not necessarily linear in excess. Okay, so anong ibig sabihin nito? Okay, see. Linear in parameters. Linahat niya dito, no? Linahat niya dito. Let me go down here. Random sampling of observations. Because conditional mean should be 0. Okay. Ibig sabihin nito, constant yung variance natin. Okay. There is no multicollinearity. Okay. And then homoscedasticity, no autocorrelation. Error terms are constant in mean, constant in variance. They're independent. All right. Example to, no? This is an example where your residuals are heteroscedastic kasi may pattern siya. Increasing over your x. No? Ito naman, decreasing over your x. This is the homoscedastic residuals. And this is what we want our residuals to display. All right, then I leave you, class, kindly read this. No? The importance ng mga assumptions na to. Okay, there's another one here which I shared with you. Let's see this. And there, of course, there are many other references that you can use. These are just samples of more explanations. Okay. So let's take a look at this. Okay. Ito klaseng yun na to, no? Okay, take a look at this. Y is equal to beta null plus beta 1 times square root of x1. This is okay, no? Yung x naka-square root o yung x naka-log, x naka-squared, yung x pwede yung x1 at saka x2, pwede ito. Linear regression models can include functions of the predictors, such as transformations, polynomial terms, cross products, or interactions, pwede yun. Okay, so that's acceptable, but not, pinakita ba niya dito? Hindi niya pinakita. But not the one where yung beta mismo yung naka-square root, naka-log, hindi pa pwede. Alright. So there's something here that, okay. Yeah, no? But there are many references that you can do. I just gave you a sample. It would be good for you to. Okay. So dito, okay, I think gamitin natin si Pacman class. Let me just. Control F. Library. Okay. So let's load these packages. You know what to do for this class. Control Alt I, and then let's use the. Of course, let's load first library. Let's load first Pacman, and then we use the pload shortcut. Control X, Control V, comma. Okay. So this is a shorter way to install packages and then load it. So I will not anymore. I will not. So kind in your case, I think you haven't loaded it. You haven't installed it and loaded it. So this will be a very good one liner to both install it and load it at the same time. And let's include load na rin natin si tidyverse. Okay. So let me run this. I need not install this because I have this packages already, and then it's done. Very quick. Very quick. So let me just test packages. Let me see, for example, Stargazer. The test already been checked already. It means it already loaded also. Okay, I'll wait for you, class, to when you have loaded it, kindly chat, please. When you're done, kindly chat, please, if you have loaded the packages. Let's wait for the others to install and load the packages at the same time using the Pacman package. Diba, ang bilis ng Pacman, ano? Hindi na tayo mag-i-install isa-isa, tapos library pa. Ito, diretso na. No? One shot na lang, install and load at the same time. There's this other package, yung librarian. Pwede rin yun. So waiting for the others to. Thank you, Jonas. Okay, how about the others, please? Feedback, please. Okay, good. Okay, I will leave you, class, to. Okay, so siguro just one, no? To study these packages, kung ano yung mga ano nila, kung ano yung mga functionalities. So let me just give an example. Kunyari, si psych package. Para saan si psych package? Tingnan natin dito. Psych, always a good source of information. Si psych naka-check na, no? Kasi ayan, procedures for psychological, psychometric, and personality researches. So although psychology siya, pero maraming functionalities to for descriptive statistics. Okay. Tingnan natin. Description, that file. So, this was updated siya ng September 12, 2022. So these are procedures for psychological, psychometric personality research. Kasi ang psych class, well, known for research talaga, no? And importante sa kanila yung ito. A general purpose toolbox for personality psychometric theory functions are primarily for multivariate analysis, cell construction, factor analysis, principal PCA, cluster, etc. So maraming statistical functionalities dito. Okay, for the site package. Let me go back here. Example natin to ha. Yung letter D, for example. Itong describe na to. Ayan o, best descriptive statistics for psychometrics. So the describe function, yan. So marami siyang gamit. Ito, example tayo, no? So I'll just run everything here. Okay. So yung data, sat.app, so this is from, tingnan nyo, ano nangyari nung ginamit natin itong describe. So take a look at this. So, andito yung mga variables, yung number nila, mean, standard deviation, median, trimmed median, mean absolute deviation, minimum maximum range, skewness, kurtosis, standard error. So you can see here that generate ang daming descriptive statistics. There. Right, so we just one line of code, which is describe. Describe daw yung sat.act data. Then yan, it generated ano yung mga measures, the count, the average, standard deviation, median, trimmed median, mean absolute deviation, minimum, maximum range, the skewness, kurtosis, the standard error, etc. Okay, so that's one way to generate quickly the descriptive statistics. All right. And there are, si Stargazer naman, tingnan natin si Stargazer. Stargazer. What is Stargazer for? Okay, Stargazer. Dapat yung sa package natin din. Stargazer. Yan, here. It's for formatting outputs, well-formatted regression and summary statistics tables. So kanina yung site, di ba hindi maganda yung output? We can combine it with Stargazer, okay, so that it will generate good summaries. For example, ito, list of summary statistics. Okay, ito. Let's see, Stargazer. May example ba siya? Okay, ito, example. Example. Run example. Okay, so hindi siya masyadong kita dito. No? Pero if we, yan, ito tingnan nyo ito. Take a look at this table below. Diba? Take a look at this. This is the output, Stargazer output. Diba maganda, maayos. Hindi katulad ng simple lang na table na, no, this gives us a beautiful, publishable output ng ito, OLS. Dependent variable, etc. Kaysa yung ano. So this is an example of Stargazer. So tinitingnan dito, may model 1 tayo, may model 2, may probit model. Tapos he put the Stargazer function is able to summarize the output and put it in a clean table. Okay? So ito yung mga lumang functionalities. Ngayon may mas magaganda pa, no, which I'll be recording that. There's this package called dlooker, which is a lot better than this. Pero so start muna, at least familiar tayo na merong package na Stargazer na makakapag-generate ng ganito kaganda. Imagine if you're going to, Excel will not give you this. Okay, ito yung sinasabi ko sa inyo, Akaike information criterion. Okay, so let's see. Okay, so let's now go to import the data set. Ito. Hindi pa natin naloload yan, di ba? Kasi take a look at the observations. Wala pa dito yan, di ba? Wala pa sa data natin. So how do we load this? Now the advantage of a project is that you can easily. Okay, so let's create this data, wage, alt minus, and then read. Okay, ayan, read. Meron tayong read.csv or read.csv2. Okay, anong difference sila? Meron ngang read underscore, ito, no? Dito na tayo sa read underscore csv. Kasi this is coming from read R, which was uploaded with, kasama kasi sa ano to si read R. Ito mas bagong ano, no? Mas bago, kasama siya sa tidyverse. So if I'm going to use this, okay, read underscore csv. Now, because generally dapat i-identify natin kung saan galing yung ano, kung saan ando dun yung ano, yung file na yan. Okay, but since it's already in our project, andito na sa natin sa file dito, you just write here wage.csv. Yan. Kasi andito na siya, no? Na-load na natin dito. So we don't have to write kung ano siya, folder siya, kung ano nasa anong subdirectory siya, etc. So could you kindly check this, class? So we're creating this object called wage. Tapos read underscore csv, yung file na yan. Let's run this. Okay. Alright. May mga notes siya dito, no? Okay, may sinasabi siya na 526 rows. Okay, nag-default siya na ang delimiter nito. Comma. Comma. Hold the line, class. Okay, sorry about that. All right. Actually, may mas ano pa, no? May mas yung if you take a look at that, kasi shortcut lang natin, we use a default, no? But if we check yung function na to, read underscore csv. Okay. So what does this do? Read underscore csv and read underscore tsv are special cases of the more general read underscore delim. Okay, so may mga example tayo dito. Ito yung kagandahan kasi ng help function ni R, no? And it will give you examples. And for example, you read from a path. You read from you can read .csv from a site, no? Ito. Okay, you can read a zip file. Tapos may iba pang ano yan, may iba pang there are many other parameters that you can use. Okay, we will not go into that now, but I just wanted to show you that these functions, yung read underscore csv, read xls, excel, these are very powerful functions that we can use when we are loading a data sa R natin. So if we check this, ito, na-load na natin, di ba? So let me view this. Yan. So we have education, experience, tenure. So there are 526 entries, 8 columns. So this is our data now. Okay, may I ask if you were able to load the data? Can we chat, please, if you were able to load the data? Okay, thank you, Jonas. How about the others? Okay, good. All right. So let's examine the data. You know, the view wage, the view function will allow us to generate a tab here. So, diba? Or if I click this, it's the same as view, diba? View wage. All right. So let's take a look at the other. What does the names function give us? The names function will give us the names of the variables. Diba? Yan. So ano laman ni wage? Education, experience, tenure. Okay, so you know the head, the tail, the subsetting. We will not run the others because we know this already. Okay, this is important to us. The structure. So let me run here the structure, wage. All right, so this the structure wage will tell us the type of data. So this is a data frame. So in fact, it's a special table. It's a data frame, but it's not a table. And as we go along, we will discuss what a table is. Okay, so here you have wage, dollar, education. You have numeric, numeric, numeric. Then you have race, character, gender is character, civil status is character, number of dependents is numeric, hourly wage is numeric. Okay. Any questions so far as the structure is concerned? Just kindly type this in your codes. No? And notice I did not give this to you because I know that you can write this already on your own. And then we can check the class of a particular or type of a particular variable. So we have here education. Okay, in fact, it gives us here the type of the class of the data. Class of wage, dollar, education is numeric. About race, race is character. And the summary of the wage is, let's take a look at the summary. Okay, let me pause for a while and allow you to catch up with what I've written here. I'm not going to explain the others like the head, the tail, and even the subsetting 1 to 10 because I know you can you understand those already. And once you're done with the summary, this one, the structure and the summary, kindly chat please so that we can discuss briefly what the summary will give us. Okay, thank you. Waiting for the others. Okay, right. So, but I'm not getting not even 90% of the responses. No? Kasi kung 90 to, dapat mga 20 yung nag-respond. But I think mga 10, 11 lang. So I hope the others are following along. Okay, so take a look at yung summary. We have for the numerical variables, it gives us, you recall the 5-number summary, diba? The minimum, the maximum, the first quartile, the second quartile, which is the median, and the third quartile, which is P75, plus the mean. Okay, and that's also for the experience, for the tenure. For the character variables, it just gives us the count. In race, 526. Gender, 526. Okay, although if you take a look at these variables, kunyari sa race. Okay, what do you think, class? What should we do with race? Should it still be just a character variable? Any suggestion? Race could be classified as what? And so with civil status and gender, what do you think should these variables be? They should be treated as? Anyone? As what class? Yeah, thank you, Jonas. Yeah, you're correct. They should be treated as factors, no? Kasi pwede silang classifiers, eh. Okay, and we'll look into that later. All right, so let's now make use of what we learned a while ago. So, tingnan natin, ha? Ito. So let's perform some descriptive statistics and let's use the psych package. Di ba may describe function dyan? So let's see, psych, okay, and then describe. Yeah, just to tell us kung saan nanggaling itong describe na to. Control Enter, and then what do we have here? Okay, you can see here an output from the psych package. This one, you have the variable, you have the count, you have the average, standard deviation, median, trimmed median, mean absolute deviation, okay, minimum, maximum, right, standard deviation, range, skewness, kurtosis, standard error. So quite a lot of measures, no? For your, of course, yung sa character variable, yung race, gender, civil status, walang notice na walang sense yung ano, walang relevance yung mga minimum, maximum kasi they're character variables. Okay, so let's take a look at another one. Okay, there's also this from the paste text package. I think we loaded no paste text package. Also a very powerful tool for descriptive statistics. So paste text package, in particular the stat.desk, parang descriptive statistics into, no? So let's use this paste text. Although pwede naman natin tanggalin na to, but just for the information of everybody, para alam natin yung stat.desk na yan from paste text. Alright, so what do we have here? Okay, parang ganun din. The only difference is that dito nasa y-axis yung minimum, maximum, range, median. Unlike dun sa describe, nasa along the column siya, no? Ito along the row. Okay, so it also computes for my variance, standard deviation, coefficient of variance, and then yung mga variables nasa along this column. And then in NA niya yung mga NA niya yung mga categorical variables, ay yung mga characters. Okay, and then here, ito, no, pwede ito, no? Here I'm writing options, 2 digits, and then stargazer natin. Stargazer natin si wage, type is equal to text, digits is equal to 2. So let's run this. Let's see what will happen to this one. All right. Notice na outline lang siya, no? Kasi hindi natin sinabi kung ano yung ipapaano natin, no? Ano yung pinapaprint natin kay stargazer. So if we include this using from the scheme R package, scheme natin yung wage. So highlight natin itong tatlong to, control enter. Then what happens now? Okay, so not so good. Hindi yung sinunod yung sa ano, ito, no? Take a look at this stargazer. All right, so naka-table siya, data summary. So the name of the data is wage, number of rows 526, columns is 8, then 3 character, 5 yung numeric. So this is coming from your scheme R. Ito, yung scheme ng wage. Okay, let me see. I think nagkamali yata ako. Dito yata dapat sa paychecks natin sinama. Let me just see. So I'm going to separate kung si paychecks. And let's see what happens if I combine paychecks and Stargazer. Okay, hindi pa rin. So, si Stargazer dapat pag used in consonance with ano, dapat ginagawa niya ng table eh. Okay, anyway, let's leave that for a while kasi hindi ko ma-decipher but the Stargazer function should allow us to come up with a very good tabular form of your descriptive statistics. Okay, so it's a time class. Let me just show you. Okay, sa regression model class, pakisulat lang to. Just to show you, chat ko dito I will end here. Let me just show you the kindly copy class sa regression model. All right, then tanggalin natin yung printout. Okay, so this is, we're going to continue with this next meeting. This is how we run a regression model in R. First, we're going to create this object. I'll just call it mod1. And then take a look at this LM. LM stands for linear model. Okay, linear model. And what model are we doing? If we take a look at wage, we would like to know the dependent variables are hourly wage, HR wage, and we would like to see how hourly wage is related with education. Okay, is hourly wage related to education? So we use this tilde. So hourly wage is your dependent variable, education is your independent variable. And then we identify here data is equal to wage. So if we run this, notice this is just a simple linear regression kasi isa lang yung predictor natin. If we run this, then you will now see that we have an object here called mod1. And this mod1 is a list. Okay, and if I use the summary of mod1, run natin to. We now have our first output for a linear regression. Okay, so this is the formula LM, hourly wage regression education. You have here a measure of the residuals. And then you have here the coefficients. I'm sure you learned this before in your previous subject. You have your intercept or beta null. You have your parameter, beta 1, education. And you can see that education is a significant predictor of your hourly wage. Okay, and then you have here, ito yung ANOVA result natin, ano? You have here your R squared, adjusted R squared, F-stat on degree of freedom 1 and 524 with a p-value of this amount. So next meeting, class, we're going to review what we have discussed and then move from here and go to multiple linear regression. Okay, so let me end our discussion for today. Stop recording.